In this video, we will review how to find the area bounded by two or more curves, and we will review how to find the volume of a three-dimensional solid whose base is bounded by two or more curves. These problems will be considered calculator active, so we will use our graphing calculator as needed. Region S is bounded by the graphs of y equals 2e to the negative x power, y equals the square root of x, and the y-axis as shown. Set up, but do not evaluate, integral expressions for the area of region S. For number 1, we must write an integral expression for the area with respect to x. So we will integrate the top function minus the bottom function. Notice that we knew that this red curve was the square root of x because we have memorized that y equals the square root of x has this shape to it. And then when you look at y equals 2e to the negative x, compare it to the function y equals 2e to the x. We know that this would be an exponential growth curve, so y equals 2e to the negative x would be a reflection over the y-axis. So it makes sense that it would be an exponential decay curve. In order to set up the integral, we will need to know the intersection point between these two curves. So let's type each of these equations into the graphing calculator. Let's hit zoom 6 and see what we get. I would like to zoom in a little more closely on the intersection area. I'm going to use zoom box. So zoom, enter, and I move the pointer to the lower right hand corner of my area of interest, and I hit enter. Then I move the pointer to the upper right hand corner of my area of interest, and I hit enter again. We can find the intersection point by hitting second trace, and option 5 is for intersection. Move the pointer close to the intersection point and hit enter as it says first curve, hit enter again for second curve, and hit enter a third time for guess. So the intersection is x equals 0.803, comma 0.896. When we set up the integral, the limits of integration from left to right will be from 0 to 0.803. And then we will integrate the top function minus the bottom function. So 2e to the negative x power minus the square root of x. For problem number 2, we need to write an integral expression for the area with respect to y. In order to do that, we need to change these expressions for each function to be in terms of y instead of in terms of x. Here are the two original functions written in terms of x. As we rewrite them in terms of y, it would be helpful to switch them both backwards. Now let's solve the blue equation for x. Dividing both sides by 2, we have e to the negative x power is equal to y divided by 2. If we then take the natural log of both sides of the equation, the natural log and the base e cancel each other out. That leaves negative x is equal to the natural log of y over 2. Dividing both sides by negative 1, we get x is equal to negative natural log of y over 2. So for problem number 2, we will refer to the blue function this way. Moving on to the red function, we can get rid of the radical by squaring both sides of the equation, and we get x is equal to y squared, and that's it. So let's replace the square root of x with y squared. When you integrate with respect to y, your limits of integration go from bottom to top, and you integrate the right function minus the left function. But be careful. In this case, the right function changes as we go from bottom to top. Below 0.896, the function on the right is the red function y squared. Above 0.896, it changes over to the blue function negative natural log of y over 2. So we will not be able to write this using a single integral. We will have to write the sum of two integrals. First, we will integrate from 0 to 0.896, and we will integrate the function on the right minus the function on the left. So that's y squared minus 0. Obviously, we don't really need to write the minus 0 part, so we can just put the integral of y squared dy. And then we move on to the second integral. For the second integral, we will integrate from 0.896 up to 2. And again, we will integrate the right function minus the left function. The function on the right, in this case, is negative natural log y over 2. And normally, I would subtract the function on the left, but that is just 0, so there's no need to write that. So I will just put dy. Number 3. Region S is the base of a solid for which cross-sections perpendicular to the x-axis are rectangles with base in S and height given by h of x equals 2x. Set up, but do not evaluate, an expression for the volume of this solid. To picture this three-dimensional solid, imagine a strange loaf of bread that is sitting on this region S, and we are looking at the loaf of bread from above. When they talk about cross-sections perpendicular to the x-axis, imagine slicing the loaf of bread perpendicular to the x-axis as shown by this little purple line. Think of this purple line as the base of a single slice. We can set up an expression for the volume of the loaf in 3 steps. First, we will write an expression for the base of a single slice. Then we will find an expression for the area of a single slice, and then we will write an integral, which is like a sum of all the slices, which will be the expression for the volume of the loaf. Step 1 is to write an expression for the length of the base of a single slice, the length of this purple segment. So that's going to be the top function minus the bottom function in this case. So step 1 is done. This is an expression for the base, 2 times e to the negative x power minus the square root of x. Next, we need to come up with an expression for the area of a single slice in terms of the base b. Remember that in this case, each slice is in the shape of a rectangle. Imagine that this rectangle represents a single slice. The bottom of the rectangle is the base of a slice, which is b. We need to find an expression for the area of this rectangle, and we know that the area of any rectangle is base times height. So it's going to be b times something. But what about the height? Well, we were told that the height of each rectangle is given by h of x, which is 2x. So the height of each rectangle is 2x. That means that the area of the rectangle is going to be base times height. That's b times 2x. So let's come back to our main expression. Right now, this expression represents b, the base of a single slice. But we need to change this and make it into an expression for area. So how can I modify this to make it an expression for area? Well, area is going to be b times 2x, and this purple expression is b. So I can make it into area by doing b times 2x. This is now an expression for the area of a single slice. The last step is to transform this expression into an expression for the volume of the loaf. The volume will be the integral of the area. When you integrate the area, you are adding up all of the slices, which gives you the volume of the solid. Since our slices are vertical, we are adding up slices from left to right. So our limits of integration will be from 0 to 0.803, the intersection point. So this is an expression for the volume of the solid. Region R is bounded by the graphs of y equals 9 minus x to the third power, the y-axis, and the horizontal line y equals 1. For number 4, find the area of R by setting up and evaluating an integral expression. Remember, you must show your setup, but you may let your calculator evaluate the integrals. Let's enter the equations y equals 9 minus x to the third power and y equals 1 into the calculator and see what this region R looks like. Let's hit zoom 6 for a first look. Region R is this area in the first quadrant bounded by the cubic function, the horizontal line y equals 1, and the y-axis. I'm going to adjust the window a bit to highlight the first quadrant. I'm going to adjust x max to be -1, and I will let, did I say x max? X min is -1, and y min will also be -1. Let's take a look. Let's take a picture of this. We are going to need the point of intersection. It looks like it will be at x equals 2, but I don't want to assume. So let's hit second trace. Option 5 is for intersection. For first curve, move the pointer as close to the intersection point as you can and hit enter. And then just hit enter again for second curve and enter a third time for guess. So yes, the intersection point is 2, 1. So here is the region R for which we need to calculate the area. We can calculate the area by integrating with respect to x if we integrate the top function minus the bottom function. So here is the top function minus the bottom function. From left to right, region R goes from 0 to 2. So we will integrate from 0 to 2. This is an expression for the area of region R. We could evaluate this by hand without too much trouble, but since we are allowed to use our calculator, let's just type it in. So we want to integrate, so hit the math button and choose option 9. We are integrating from 0 to 2. And we are doing 9 minus x to the third power minus 1. So 9 minus x to the third power minus 1. The area is 12. Number 5. R is the base of a solid for which cross-sections taken perpendicular to the y-axis are squares. Set up, but do not evaluate, an expression for the volume of this solid. Every time I mention the solid, I want you to picture a strange loaf of bread that is sitting on top of this yellow area, and we're looking at it from above. For this problem, we will be calculating the volume of this solid by adding up slices that are perpendicular to the y-axis. Calculating the volume of a solid is a three-step process. First, you write an expression for the base of a single slice. Then you transform that into an expression for the area of a single slice, and then you integrate the area to find the volume of the solid. Because the slices are perpendicular to the y-axis, to find the volume we will be integrating with respect to y. Therefore, we need to rewrite the cubic equation in terms of y. To begin with, we have y equals 9 minus x to the third power. Adding x to the third power to both sides and subtracting y from both sides, we get x to the third power is equal to 9 minus y. We can get x by itself by taking the cube root of both sides of the equation. So we end up with x is equal to the cube root of 9 minus y. So this is the expression that we will use when we refer to the cubic function. We can write an expression for the length of slice B by doing the right function minus the left function. The function on the right is the cube root of 9 minus y, and the function on the left is 0. So an expression for the length of the base of a single slice will be the cube root of 9 minus y minus 0. Obviously, we don't actually need to write the minus 0 part, so I'm just going to erase that. Step 2 is to transform the expression for the length of the base of a slice into an expression for the area of a slice. We are told that the slices are all squares. So if the base of a slice is b, then the area will be b squared. So if this purple expression is b, I can turn it into the area by squaring it. So that's step 2. This is an expression for the area of a single slice. The third step is to make an expression for volume by integrating the area. When we integrate the area, we are adding up all of these slices of area to form the volume. So we are integrating from y equals 1 to y equals 9. So those should be the limits of integration. So that's it. This is an expression for the volume of a solid sitting on top of region R.